Welcome, folks, to another exciting AP Chemistry video lecture. Our focus this time is going to be starting Unit 8, in which we are going to be discussing acids and bases. And for this particular video, our focus will be on the introduction to acids and bases, as well as pH and pOH of strong acids and bases. A few things to keep in mind with this particular content is that some of this will be review. As you know, we have covered acids and bases in the past. Even this year, we've covered a little bit on what is an acid and a base reaction, as well as conjugate acid and conjugate bases. Furthermore, it's going to be very important, especially as we approach the end of this unit, to really be thinking of these reactions in terms of equilibrium. When we get to weak acids and bases, they really act in equilibrium as opposed to strong acids and bases, which tend to fully go to completion. So we'll need to keep in mind things like the equilibrium constant and Le Chatelier's principle as we go through and complete these unit activities. By the end of this video, you should be able to discuss acids and bases and identify strong acids and bases. You should be able to explain the autoionization of water and how temperature impacts the pH of pure water, as well as calculate pH, pOH, hydronium ion and hydroxide ion concentration from given values. Now, recall and reflect on what acids and bases are. Acids are proton donors and bases are proton acceptors, at least for this class. So in looking at the reaction below, we see that HCl donates its hydrogen to water, thus making HCl the acid and H2O the base. We'll talk more about conjugate acid and bases here in just a moment. Now, the strength of an acid or base is related to two factors. One, whether it is classified as a strong acid or base, which we'll talk about in a moment, and also the amount of concentration of hydronium or hydroxide that is placed into solution. These two factors indicate the strength of an acid or a base. Let's recall and remind ourselves of conjugate acid-base pairs. Acids become conjugate bases when it loses a hydrogen. For example, H2SeO3 donates its hydrogen in the reaction to become HSeO3, the conjugate base. On the other side, bases become conjugate acids when it gains the hydrogen. So C6H5NH2 accepts a hydrogen from the acid, thus becoming C6H5NH3+. It is very important and critical to be able to identify these acid-base pairs. Now, we've talked a little bit about this in the past, so I'm not going to go into as much detail in it as I probably would with a generic chemistry or general chemistry class. We know that expressions of hydronium ion and hydroxide ion concentration are typically times 10 to the negative something, and these numbers can be difficult to work with to determine how acidic or basic a substance is. So rather than using those numbers, we put it on a base 10 scale using logarithms. And so in this case, we are looking for things like pH and pOH, and to find those, we just take the negative log of the concentration of H if we're finding pH, or the negative log of the hydroxide concentration if we're looking at pOH. Now, in a neutral solution, at 25 degrees Celsius, pH plus pOH equals 14. I'm not showing that specifically here for a reason we'll talk about in just a moment. Also, if we want to go to the reverse of that and find the hydronium ion concentration or the hydroxide ion concentration, we just use the inverse function of log, which is 10 to the power of. So I would take 10 to the negative pH to get my hydronium ion concentration, and 10 to the negative pOH to get my hydroxide ion concentration. Now, when we look at a pH scale, again at 25 degrees Celsius, anything lower than 7 is considered acidic, which means that my hydronium ion concentration is greater than that of my hydroxide ion concentration. If my pH is higher than 7, it is considered basic, because my hydroxide ion concentration is greater than that of my hydronium ion concentration. And at a pH of 7, we consider it neutral, because hydroxide ion concentration is equal to hydronium ion concentration. Now, again, this is only at 25 degrees Celsius, and we're going to talk about why here in just a moment. There's a concept that we need to understand. This is going to be something a little bit different than what we've talked about previously, is that water self-ionizes, meaning that it reacts with itself to produce one hydronium ion and one hydroxide ion, as you see down below. Because this goes back and forth, this is at equilibrium, and we have an equilibrium expression that we associate with that. The K value for this is 1 times 10 to the negative 14th, which means that at equilibrium, we strongly favor our reactants. Remember that a K value that is less than 1 favors our reactants, and a K value greater than 1 favors our products. We can write the equilibrium expression for this as 1 times 10 to the negative 14th equals the hydronium ion concentration times the hydroxide ion concentration. Remember that liquids and solids do not participate in the equilibrium expression. So essentially, if we know the concentration of one, we can solve for the other. And again, this is at 25 degrees Celsius. If you recall, K value differs based on the temperature and whether the reaction is endothermic or exothermic. Let's take a deeper look. So as I look at the chart on the right-hand side here, I have a value for temperatures, and I have a value for Kw. So based off of this information, we can determine if water autoionization is an endothermic or exothermic process based off of the values of Kw at different temperatures. So take a look there and think for a minute. Notice that as the temperature increases, the value for Kw increases. So that plays a really huge role in determining what the reaction does. If the Kw increases, what that tells me is that it favors more of my product production than my reactant. So that indicates that this is an endothermic process. Thus, we would put heat on the left side of the equation if we were to look at this from a equilibrium perspective. As we increase heat, as we increase temperature, Le Chatelier's principle states that the reaction is going to shift to the right, increasing the hydroxide ion and hydronium ion concentrations. So what are the key points I want you to take from this? Well, in pure water, regardless of temperature, pH is going to equal pOH. The pH of pure water is only 7 at 25 degrees Celsius. As the temperature increases, the pH of pure water actually decreases, because again, it is an endothermic process. As we add more heat to the left side of the equation, that causes a shift due to Le Chatelier's principle to the right-hand side, thus producing more hydronium ions, thus making the solution more acidic. We're going to start off just simply by looking at strong acids and bases. Keep in mind that strong acids and bases completely dissociate in solution. What that means is that they 100% ionize, meaning that they 100% break apart when you put them into solution. So it makes it very easy to determine the hydronium ion or hydroxide ion concentration from this information. Your strong acids include hydrochloric acid, hydrobromic acid, hydriodic acid, nitric acid, sulfuric acid, and perchloric acid. Your strong bases include groups 1 and 2, that is your alkali metals and alkali earth metals, plus your hydroxide ions. Therefore, the concentration of the solution can be easily calculated. Because, for example, if we know that we have 0.1 molar HCl, and we know that it 100% completely dissociates in solution, then my hydronium ion concentration will also be 0.1 molar. Same thing works for hydroxide. If I have 0.1 molar NaOH, I know it completely dissociates into Na plus and OH minus, then I know that I have a hydroxide ion concentration of 0.1 molar. Be careful though, especially with group 2 bases, because 0.1 molar CaOH2, remember that for each one of those that breaks down, I'm going to get 2 hydroxide ions. So my concentration of hydroxide is going to be twice that of my original concentration. So let's look at a couple of simple practice problems that we can go through and figure out. Question number 1 asks, what is the conjugate base of HSO4-? Well, in this instance, we're assuming that HSO4- is an acid because it's asking for the conjugate base. And recall that when an acid becomes a conjugate base, it loses its hydrogen. So therefore, the conjugate base of this is going to be your sulfate ion, letter B. The next question asks, what is the concentration in molarity of hydronium ions in a solution at 25 degrees Celsius with a pH of 4.282? Well, we can plug this in using the inverse log function, 10 to the power of, and be able to solve for the hydronium ion concentration. So we put the concentration is equal to 10 raised to the negative pH. We plug that number in, and what we get is 5.22 times 10 to the negative fifth. Remember, these are concentrations, so you're going to want to use molarity. Lastly, it asks, what is the pH of a 0.015 molar aqueous solution of barium hydroxide? Well, remember that to start off with, barium hydroxide is BaOH2. So that indicates that the concentration of OH ions is going to be double that of our concentration of our solution. Well, if we know the concentration of OH, then we can solve for the pOH by taking 10 to the negative log of the concentration. Once we get that, we can then, again, subtract it from 14 and get 12.48 to be our pH. So, in retrospect, there's also a couple other ways that we can look at these problems to solve them. You have a pH of an aqueous solution of a very strong base. So that tells you that it cannot be B or D because bases have a pH that is higher than 7. Using little tricks like this are going to be very helpful for you in figuring out how to solve for a variety of different pH problems. Hopefully now you are able to discuss acids and bases and identify strong acids and strong bases. Another key critical point here that separates AP from general chemistry is explaining the autoionization of water and how temperature impacts the pH of pure water. And then lastly, make sure you can calculate pH, pOH, H3O+, and OH- from given values. I appreciate your time. Thanks for watching. Have a great day, and we'll see you soon. Bye-bye.